All right. Hello, everyone. So I know some people are still joining, getting situated. So hello to everyone from around the globe. I'm Susan Satardi, Assistant Professor of Radiology at the Children's Hospital of Philadelphia, and your moderator for today's webinar. So welcome to this month's AI webinar, which is Transformers and Bio-NLP, Transforming Words into Care. So thank you to the SIIM Machine Learning Education Subcommittee for their organization and support of this webinar. So this webinar, just to remind you, is eligible for 1 hour of SIIM IIP credits that can be used towards your ABII SIP certification or recertification. And to receive credit, you must be a SIIM member and attend at least 45 minutes of this webinar. And just to remind, please ask your questions using the Q&A icon on the Zoom menu throughout the webinar, and we'll work to answer them after the talk. So I am very excited to present alongside my amazing colleagues, Parsa Begersede, PhD from postdoctoral research fellow at McGill University, and Farhad Maleki, PhD assistant professor at the University of Calgary, who is also my fellow member in the Machine Learning Education Subcommittee at SIIM. So without further ado, let's get started. All right, so many of us are increasingly familiar with machine learning and specifically deep learning architectures such as convolutional neural networks. However, in the news, I'm sure you've heard, and also in the literature, are models which use what's called transformer architectures. And these models have been widely used and established in natural language processing fields, which are concerned with modeling of language elements. The transformer model, which has gotten a lot of press recently, GPT forming the backbone for ChatGPT. However, there are lots of other widely used neural network processing algorithms which use a transformer architecture. And recently, progress has been made with transformer models being applied towards vision tasks and image analysis. So what is a transformer architecture? Well, at its basics, it uses an encoder and decoder to take in a phrase such as, "I like robots," and then convert it to the French version. So the encoder takes in a word and then predicts the next word in the output sequence. And the decoder then generates the output. But in reality, this process is way more complex, and the word inputs are iterated through numerous encoder layers. The encoders really create these encodings, which define the pieces that are relevant to one another, passes to the next encoder layer until eventually the outputs are fed into the decoder, which takes in the encodings and uses the context to generate output probabilities. And really a large part of transformer architecture relies upon a process called attention. And in many cases, such as the foreign language translation task, these words cannot be processed in sequential order while maintaining the same meaning. So attention allows us to see what components of the phrase carry the most significance, and then try to use the context in order to inform the predictions. So in order to provide kind of a basic framework for attention, we'll start with a sentence which is composed of n number of words. So for each word, we're going to get 3 vectors: the query, the key, and the value vector. Next, we calculate the score for each of the words using the dot product of the query for word 1 and all of the other keys in that sentence. We then normalize these scores and apply softmax to create the logits. We then use these scores to scale the value vector, sum up these values, and get an attention vector for each word as the output of the attention layer. All right. And while to some extent this oversimplifies things, these concepts are really at the heart of a lot of the progress that's been made in transformers, especially as they apply to language processing models. So to come back to our friends, the convolutional neural networks, as an imaging community, we like to think about how these machine learning concepts also relate to images. Obviously, text analysis is an important part of what we do, but from the image perspective, up until the last few years, image analysis was really dominated by convolutional neural networks, which we know pass weights with information about an image through multiple layers in order to predict the outputs. And a common use case, as we see here, is to use a pre-trained neural network such as ResNet, and to finally train the network on a specific input such as X-rays of the lungs, and then predict at the end whether it's normal or abnormal. And while convolutional neural networks alone definitely have utility, transformers leverage the attention mechanism that we spoke about previously to really improve upon these results. And so one of the new kids on the block are these vision transformers. So the seminal paper by Dosovitsky in 2020 demonstrates how vision transformers can be used for image analysis. And the first step in their model was to split the images into patches, as you see here. And then they use these patches as inputs into the encoder, analogously to the way that we were using words in the NLP application, in order to then train the transformer on image classification tasks. And the outcomes of this analysis are very promising. The team found that the vision transformer performed better than convolutional neural networks, particularly with respect to accuracy and computational efficiency. However, the biggest downside was really that these models appear to perform much better on very large data sets, which result in truly massive numbers of parameters for the network to deal with. So for example, JFT 300M has 18,000 classes and 303 million high-resolution images. So in its current state, the size of the data sets and the computational cost of using transformers for image analysis creates some really formidable barriers towards using them in the clinical environment. However, we have hopes that with time and investment into these architectures, more options will be available in the image analysis space. So with that, I will turn it over to Parsa, who will be discussing some of the important aspects about natural language analysis.
Thank you, Susan. You need to stop sharing so that I can, okay. So, hello everyone. Thank you, Susan, for the introduction. So let's talk about natural language processing. What is NLP? Basically, NLP is the one of the subfields in AI that enables interaction between computers and human languages. NLP basically allows to and gives the machines this ability to understand, interpret, and generate human language. One of the most significant and prominent examples is ChatGPT, that basically generates human language. And so NLP uses different and various methods, from computational linguistic, which involves the linguistic aspect and linguistic processing of natural language, looking at the linguistic structure of language, as well as machine learning and semantic theory to interpret text. The result of a natural language processing pipeline is basically to allow us to process and analyze a large amount of unstructured text. So when you are talking about unstructured textual data, one of the examples and instances is a clinical report. Clinical reports, in fact, are one of the nastiest unstructured data available to medical community. Clinical reports are an essential component of EHRs, electronic health records, which contain very important information such as patient's medical history, even information about their families, comorbidities, what other diseases they had before, symptoms, physical findings, prescribed drugs, so on and so forth. So together and in conjunction with imaging, they can be used for a better interpretation of patients' status, and such clinical reports in form of text. They provide some sort of context for to interpret images. One cannot interpret phenomena in isolation. It should be interpreted together with the context. It also allows to identify health issues that might not be apparent only from the images, to give a basically complete picture. So talking about NLP tasks, what are the most important tasks in NLP, specifically, for instance, for biomedical domain and medical domain? One of the most important tasks in NLP is named entity recognition, or NER. So this task involves classifying and categorizing different entities, named entities into these predefined classes, such as drugs, diseases, biomarkers, so on and so forth. For instance, here, this is a clinical report that different entities are annotated here. For instance, what type of imaging was there, what kind of diseases or respiratory diseases that they were mentioned. And also, it is really important for the name and recognition to look at the context of the report. Why? Because in isolation, consolidation is not a disease, but in fact, this is long consolidation, looking at the context. So and name recognition can also predict, for instance, drug mention, and even going further, it can we can find doses that are prescribed doses. How many times, for instance, twice a day, how many times. So once these information are extracted, these information can be used in downstream tasks. For instance, to find the correlation between a specific dose of a drug and the outcome of a treatment. So usually name and recognition is the first step in an information extraction pipeline. An NLP pipeline, it includes different stages, that each of these stages usually takes the output of the previous stage, and gradually we would have a more complete picture. Next, we have co-reference resolution. Looking at clinical reports often involve ambiguous references in the text. For instance, here, this is a sample report that talks about chronic obstructive pulmonary disease. Later in this piece of text, we have COPT that is referred. We have another entity COPT. So if we look at this text, this COPT refers to this entity that was previously mentioned. So the task of co-reference resolution is to basically identify mentions that refer to the same entities in the world, or in this case, in this clinic, for this patient. So first, we identified the named entities in the previous stage, such as chronic obstructive pulmonary disease and COPT, and then we try to resolve these ambiguities and basically link these entities. Next, we have relation extraction. Once these entities are identified and their references and the co-references are disambiguated, we need to extract the relations between these entities. So usually when you're talking about relations, we are talking about events, what kind of events are happened, and what caused what, or what was revealed by what. For instance, this this entity revealed what? Revealed a disease. So this imaging, this test, as a finding of this test, we can associate this disease as a finding of this test. So we have a relation between this disease and this imaging. This is really important for clinical reports. Why? Because they often contain very complex information that are provided. So the theme of my talk is actually low-cost information extraction, because anybody can have a large set of training samples, gather many samples, and then train a deep model or a machine learning model, and then be happy with it. But the point is, in medical domain, it is really expensive to obtain the gold labels, because these samples need to be labeled with highly trained experts. So the solution to this can be seen in more old-fashioned approaches, as well as new type of approaches. So here we are trying to marry old-fashioned approaches and new approaches. So, for instance, how can we extract information without annotated data from a piece of text? If we go back to the old-fashioned linguistic processing, as I mentioned, many of the events they are described with a specific linguistic structure. For instance, they are described by subject, verb, object constructs. When I'm talking about subject and object, so if we answer this question, that who was the subject and what was the object, we can extract valuable information from the clinical reports, because these are the events. So, for instance, this is a piece of text. We saw this before. We can run this piece of text using available syntactic analyzer tools, such as dependency parsers, and this gives us syntactic information of who is the subject. A scan is a subject. A scan revealed what? The presence of something. So the question that we are answering here is that who did what to whom. Okay, these triples, these structures, they can provide many information for us without any training data, just by relying on linguistic processing and the language information. Another sort of information that we can use to our benefit is the existing medical knowledge sources. So when I'm talking about knowledge sources, I'm talking about terminologies, the high quality terminologies that are curated using by experts of domain. Usually these knowledge sources that are describing terms in a domain of interest, here medical domain, using some sort of a graph, that each node in this graph represents a term, and each arc in this graph represents a relation. For instance, Lenvima is a drug that treats thyroid cancer, which is also an inhibitor of VEGF, and thyroid cancer is neck cancer. So what is the benefit of using a knowledge source is that we can expand the coverage of NLP systems beyond what is actually mentioned in the text explicitly, and also what is seen in the training data. For instance, and also we can infer additional information from the clinical text. For instance, if you are interested to see, for instance, what drugs are used for neck cancer overall, although in the or what drugs we have used in this institution or in this hospital, overall we can use it and infer more information. One of the examples of this, and one of the samples of this instances of this medical knowledge sources, is UMLS, Unified Medical Language System, which is provided and maintained by U.S. National Library of Medicine, NIH. UMLS again is a knowledge graph that integrates more than 200 medical ontologies from different languages. For instance, you see here the entry for chronic obstructive airway disease. This has many different entries in it, and you can see we even have entries from Japanese and Polish. So this allows to extend the applicability of existing medical systems to multilingual settings. As you can see, it provides different synonyms for this term, and we can use these synonyms to our advantage, and for instance, use it for co-reference resolution. The samples that I had before here, I had COPD and chronic obstructive pulmonary disease. You see that these two terms, COPD and chronic obstructive pulmonary disease, they are appearing under the same entry, under the same term. So far, I talked about more old-fashioned approaches when we don't have much of a training data. So we can use these old-fashioned approaches to expand the coverage of our NLP systems. But how about new methods? So one of these methods and paradigms that we recently have is contrastive learning. So the contrastive learning, the idea is basically to learn similarities between and differences between pairs of samples. For instance, here we have 3 scans of lung. Here we have two normal scans and one with squamous cell carcinoma. So we know that these two scans are normal, and this is these two are similar, and these two are not similar. So the task of contrastive learning is to basically find an encoding of these samples, find a representation of these samples, such that the distance of the two unsimilar or dissimilar samples are maximized, and the distance between two similar samplers are minimized. And basically, in the vector space, they are placed closer to one another. So so what is the outcome here? The outcome here is that it yields representations that are invariant to certain transformations, such as affine transformation or certain rotations. And we want our systems to provide robust representation, specifically in the medical domain, that we have many noisy samples, many noisy images, many noisy text. Everything is noisy. So, but the point is how we can bridge, how we can use contrastive learning and bridge between textual data and image data. This is the question. So in medical domain, we usually have pairs of images and text. So a radiologist, they often write down their diagnosis or write down a description of the image. So we can use this to our benefits. So we have these pairs. We give the image to a vision pre-trained model. For instance, a model that is pre-trained on AlexNet or ImageNet or a general domain. But the point is, this vision pre-trained model does not provide a very rich representation, a good representation for this medical image, because the domain of pre-training was different. So we want to use these textual reports to actually refine and enhance the representations provided by this vision model. So we project representation provided by this into an arbitrary space. We give the representation of this textual representation to a language model. Again, we have a representation. We are projecting this to the same space. Then we want to minimize the distance between these two in the vector space, because one can argue that these two are basically the same. These are the same representation for two different representations for same phenomena. Okay, and then we do the training, we backpropagate through this contrastive loss and update the parameters of this vision transformer. Now this vision pre-trained model, for instance, it could be a vision transformer that Susan talked. We can then fine tune it for our downstream tasks. This has now better representations. But We can also go further. We can also use this contrastive learning for retrieval. How? Again, we have pairs. Again, we have pairs of images and text. We have, for instance, histopathology of slide images, and we have pathology reports. We know we have learned similarity function between, or now we can know that which image is closer to which textual report. We can use this to our benefit and provide an image in a clinic, for instance. We are interested to see who are the patients that have the same similar condition to this image, for instance. We provide an image as a query, and we have a candidate. We have a set of candidates of the clinical reports. It retrieves the clinical reports that are similar to the patients that had this histopathology image. Or we can provide a textual description as a query and retrieve similar images. So we can use this contrastive learning for retrieval. We can also go further and basically use these ideas to do classification without even training a classifier. This is too good to be true, but it is true. It is applicable. So we can the same way that we had before. We can train a system with contrastive loss, try to minimize the distance between this image and this text, their representation, their respective representation. And then in the test phase, we have an image. We can provide two prompts. If we are interested, for instance, in the seminal vessel, we can say positive something or negative something. So we have two prompts. These can be easily encoded through the language model, and then we see this image is closer to which prompt, to positive or negative. Whatever it's closer or whatever is similar, we can assign this image to that class. So this enables not to be limited to the classes that are actually provided in a training data, but it provides a more flexibility to us. So at the end, let me provide some statistics on contrastive learning research. In the past 10 years, we have seen, we didn't see much of our research in contrastive learning for medical data, but in the past maybe 3 years, we have seen a jump for the medical data. It shows that there are still rooms for improvement and for research, and specifically for medical images, we see that only 80 research paper was published in 2022, and so far we have seen 50 papers. So the projection for the next 6 months maybe would be 100. So we would see an increase. So in conclusion, there are two avenues for low-cost information extraction, and we can leverage textual reports with two major approaches. One, to use medical knowledge sources and linguistic information, and the other one is the contrastive learning, which can benefit the predictive system, medical predictive system. But the point is, contrastive learning models for medical data still are at their infancy, and I believe active collaboration between machine vision and NLP communities is needed to address the gap in medical data analysis. So it's time to don't see NLP community as your enemies, and I believe in the NLP community we shouldn't see vision community as the enemy like we used to do, but it's time to join forces and address these gaps. So basically that concludes my talk. So now Farhad.
Yeah, thank you so much, Parsa, for that beautiful talk. So we'll turn it over to Farhad. And
yeah, perfect. Thanks again, Parsa. So far, we heard about brilliant applications, and one theme common between these applications in the medical domain is the challenge we are facing in the medical domain, and that's annotation. Annotation of medical data is difficult and challenging. So why these days we see a lot of progress mainly because of techniques that allow us to train models using a huge amount of data. Imagine if you want to label almost every textual data that you can find on the web. And this labeling, of course, is not scalable. It's not doable, even when the data is not highly technical. So consider the challenge that you are facing when you want to annotate a lot of data in a technical domain. That's definitely one of the bottleneck. And many of you might have actually some experience with data annotation, laborious, difficult, and also something that's most doctors, most medical experts might see why I should not focus at this point on my patients, because that's the area that we are, all of the medical experts are under pressure. This is a skill that's highly in demand, and we are actually suffer from shortage of medical expertise and access to medical care. So self-supervised approaches actually help with us to bridge this gap to some extent. What this self-supervised learning give us is to actually use the input data as a source for supervision. During self-supervised learning, as the name suggests, you don't need to annotate data manually, but we annotate data computationally. For example, in the context of transformers, you have sequence of text data. You mask some of these words and try to predict it. This way, this process of creating annotation is done completely computational, in a computational manner. So self-supervised learning approach actually help a lot with data annotation and making it possible to train complex models with a lot of data, but without actually that much manual annotation. They also have a characteristic that most of the time are underlocked. When I give, for example, for a radiology image or CT image, for example, if I give a binary label for a tumor, for example, benign versus malignant, I give one bit of information per each image. However, there are a lot of more information that actually can be transferred and used for training this model. Self-supervised learning approaches try to discover the underlying structure and patterns in the data and make it possible to benefit from those. Common pattern that we see when utilizing self-supervised learning, more specifically in the imaging domain, is that we use self-supervised learning approaches, pre-train a model, and when this model is pre-trained, we can actually transfer what we have learned in the first phase and apply this self-supervised model to the model or the problem that we are interested. Of course, for the second phase, we have some training data, some labeled data, and some of them might be manually labeled. But the point is that the features learned during the self-supervised learning is actually very helpful and make it possible to train a high-performing model with a small annotated data set. So that's something to have in mind. For this rest of this presentation, I focus on this slide. You see a lot of natural images, but I want to highlight that most of the content, or if not all, are completely applicable to all images, including CT and MRI images that we see usually. So how this process actually happens during self-supervised learning. So we talked about computationally annotated samples instead of annotated data. One approach was actually came up was computational labels. So I go with one example. For example, if I have an image, if I rotate this image computationally, it is a very straightforward process to do computationally. And since I know how much this rotation has happened, the degree of rotation also give me a label. So given this information, I actually have an image with a label. This label we created computationally. Using this pairs of image and label, I can actually train a model and try to try to predict the computationally generated label. And to be able to do this, the model needs to learn context about the data or distribution of the model I have. So that was one example. Can I do other examples to create other approaches to create annotated data? Yes. For example, here I use a approach, we refer to it as image painting. If I hide or mask a part of the image, a human artist might be actually able to predict and annotate or let's say paint the rest of the image. The same actually go with medical imaging. So what I do here, I have the image as input. I mask that. Since I have the original image, I can actually, I have access to the mask parts, and this gives me a pair for training the model. One area that you can also see is if I have a grayscale, if I have an image, I convert it to a grayscale image computationally, very straightforward. And given the grayscale image to the model, I need to predict the color. So this approach might not be applicable to CT or MRI images, but is applicable to other medical images like retinal imaging, for example. Is there any other pretext task? Yes, perhaps there are other tasks that you can pretext tasks that you can come up to create this computationally generated labels. Here you see an image. I create a puzzle from this image and I shuffle this. And the purpose of the model is that if I give the model a shuffled version, the model actually should be able to come up with a correct layout of these, let's say, shuffled crops. This way, the model, in order to learn the correct order, they need to learn how, for example, in this case, how a lion actually look like. And understanding those features are very helpful for downstream tasks. Contrastive learning was something that covered, and I just wanted again mention. In contrastive learning, what we need is actually to come up with a similarity and dissimilarity. Images that are similar should be, let's say, coded in a coding language that are similar in a different space. For example, if we encode this in each image with as a vector, this vector should be, for two images that are similar, this vector should be close to each other. And how to define the concept of close, the two things being close, two vector being close, there are many similarity scores and functions or metric function that you can use, including Euclidean distance, for example. So in this case, image of two dogs should actually lead to two vectors that are distance-wise closer, but images of a dog and an elephant should be actually far from each other in a embedding or in that coding space. This concept can be generalized to other types. For example, for tumors, benign tumors should be closer together in the embedding space, while benign and malignant tumors should be far apart in that embedding space. And by embedding, I mean the vector that the model actually give us as output. So this approach actually have shown that we can, through these, let's say, self-supervised approaches, reach a performance which is on par, and in some cases even better than supervised learning approach when we train a model based on a large number of annotated data, manually annotated data. Okay, having that in mind means that we should be able to actually benefit from this approach in medical domain and expect to reach a performance comparable to many large-scale models. Perhaps recently you have heard about diffusion models. Some of you might have heard about models like DALL-E. These models actually provides you provide them with textual information, and they give you a image that's that shows that text very in line with the text. This has been a huge progress, and actually recently is a hot area in the machine learning or computer vision domain. I don't want to cover generative adversarial network. Some of you might also be familiar in GAN models. Also, we rely on data without annotation. Those are also a subcategory of self-supervised learning. But diffusion models that are a recent progress actually in the vision domain is we have seen that they are capable of generating synthesizing images that are way better compared to the images that we actually can create with GAN. For example, in this chart on the left, you see images generated by a GAN model. In the middle column, you see generated by the diffusion model. One common pattern that you see is that for GAN models are good at generating the distribution. However, they fall short when we want to see some anomalies. For example, if you look at many of these images generated by GAN, they show less variability, and they show those patterns that happens again and again. However, the diffusion model actually work better in creating and generating the data that are not the average, the common pattern that shows up in our data sets, something that we need for medical domain more specifically. What is the key area, or key idea actually behind the diffusion models? So these models are built on one simple idea actually. Through systematically destroying the structure of data and then trying to learning a reverse process to restore the structure of data. So we have two phases. In the first phase, actually, we try to add a noise to the data. From the initial image, we get actually a completely gradually add noise till we get a complete noise through the data. And when we are at that stage, we can go back from the noise and try to predict the original image. So that's the key here. So we have two phases. The forward diffusion. Through the forward diffusion, actually we add a noise gradually. So we start from the image and then gradually add noise. At some point we have shear noise. So the forward phase is something that we do it computationally. This gives us a lot of examples that later can be used for model training. In the backward phase, however, we have a deep learning model, and this deep learning model tries to, given each image at each stage, try to find or predict the model with less noise. And finally, given the last version, you can achieve the initial image. So this process doesn't require any manual annotation. You create a lot of sample pairs for model training. And this simple approach actually has been behind many of the progress recently in the computer vision domain. And we will see more and more in the medical domain as well. So having said that, the self-supervised learning approach has a lot of potential for this field, and we will be able to actually leverage these techniques for medical domain, because first of all, one big bottleneck that we have is data annotation. In addition, unlike natural images that are very way easier, actually, way easier to come up with a label for image. For medical imaging, there are inter-observer and intra-observer variability. So there might be disagreement. This make the labeling process more challenging. However, these approaches allow us to provide labels for samples that's for images more specifically that have no technically, or labels are not incorrect or ambiguous. And that's a key concept for training a high-performing model. Having said, I pass the presentation back to Susan for Q&A. Thank you.
Thank you so much, Farhad. That was wonderful. Let me go ahead and share my screen. Okay, hopefully you are all seeing the correct screen. So thank you both so much for your wonderful presentation. So we'll be moving to the Q&A portion of the webinar. During this portion, please ask questions using the button below, the QA button in the Zoom panel. I also wanted to remind you that IIP credits will be issued to the SIIM accounts in the coming days. SIP members, if you'd like to take advantage of automatic credit transfers, please include your date of birth and ABII number in your profile when renewing your membership. And also, we'd like to make sure that you know about the SIIM annual meeting from June 14th to 16th in Austin. It's the go-to destination for imaging informaticists to discover the latest enterprise imaging technologies and solutions, and it's where vendors and users are coming together to innovate. So please don't miss your chance to spend 3 days with us. And then also to remind you about SIIM. So please submit your abstract to this year's conference on machine learning that will be held in Johns Hopkins in Baltimore. The deadline is July 12th. So there's the QR code if you'd like that. And please take our post webinar. So, for the QA session, I'm just going to take a look and see if anyone, oh, great. So John Mongan has asked, if there's a recording available, and yes, there will be a recording that will be available. And an anonymous attendee had asked, mentioned that transformers for vision are more computationally efficient than CNNs, but also more computationally intensive. Could you explain this further? So the number of parameters that's generated with transformers is definitely a large number now. So when we get into saying like, well, how big is the convolutional neural network that you're comparing it to? The issue is really that in order to get up to these numbers where we start to see an improvement in transformers relative to CNNs, you really do need to have millions of inputs and potentially tens of thousands of classes. So that's where it gets to be a problem. It's not so much that the transformer inherently has to have more parameters, but that when in order for it to learn better, we need to see it with these really, really large data sets. So that boost that it gets above the CNNs, it's requiring a level that would be hard in the clinical environment to support. I had a couple of questions for the panelists. As we're in the clinical informatics world, Epic recently mentioned to us that they're going to be integrating GPT-4 into their electronic health records. And I would love to hear, Parsa and Farhad, your thoughts on that. I have my thoughts, which I'm happy to share as well. A lot which sort of relates around some of the technical issues, things like catastrophic forgetting, where it completely just forgets things that it learned. You then end up having to have these data streams that are enormous in order to maintain that level of knowledge in the system. And then there's all sorts of other downstream effects, but I'd love to hear from both of you what you think some of the issues might be if we bring this into the clinical space. Are we ready?
Parsa, do you want to go first?
Okay, so one of the main concerns that most of the hospitals and institutions they have is the data privacy. So I believe that there would be some hesitation to allow the data to go outside of the hospital, like medical history and written narratives like this. And it's not like that these models are so small that one server in the hospital, they can be dedicated to these models and then use these models in-house. So most of these models that are very large. If hospitals wants to use these models, they need to be used throughout APIs. The data should go out of the hospital. So this is a real challenge here. So this is first this, and although there are these models like ChatGPT, they're performing fantastic. Their performance is fantastic on general text. There are still rooms for medical text. These models they have significant serious challenges and issues like hallucinations. Usually they are very good for inferring information within text. Okay, so if you ask a question, what's happening in this text, they are good. But if they want to generate something about this text or further information or more knowledge out of this text, sometimes they hallucinate. 2 hours ago, I was in another talk. I was attending another talk that was they were talking about retrieval of PubMed articles. The question from ChatGPT was to give me a set of symptoms for COVID, together with the PubMed ID and the reference. So the symptoms were correct. The general knowledge for this was correct, but it returned fake articles. So no such article existed. So yes, it's fantastic. It's a fantastic tool for general domain. But when we are talking about medical domain, we have established knowledge and knowledge sources in medical domain that I believe those knowledge sources need to be integrated, like I talked about UMLS, for instance. We know that COPT, what is COPT. We don't need ChatGPT to tell us what is COPT. We know what is Lenvima and what is how for what it is used and for what it is prescribed. What are the associated conditions? We have this high quality image, high quality information, modeled and curated by the domain of experts. And I believe that there need to be an integration. These explicit knowledge sources need to be integrated. So that's basically my but from a privacy point of view, we are still a little bit far away from that.
Yeah, I also add that the challenges that we face in deploying these models in a clinical environments are, I would go with two main category: technical challenges. So models like transformers, they are computationally efficient in a way that we can parallelize them. So that's since they don't have that sequential nature, so that's very easy to use high computation to deploy them. However, that high system with high computational power has some cost. So that's one challenge, but I think that's as we move forward, one big push in the AI community is to come up with models that are lightweight and more accessible to a large, groups. There are many countries, actually, they might not have the resources that here we call it expensive, but we can afford it still. For those are not an option. So that's one thing that down the road, I see that to be solved. It takes time, but it will be a challenge that I foresee down the road. We'll solving it very efficient. Maybe in a couple of years, that won't be a challenge. The other category of issue we have actually is regarding patient privacy. If, for example, if we are deploying ChatGPT, is this how the data is actually processed? Do they use the data to improve their model? This means that to some extent, they can pick up information from the patient record. As we saw something actually recently in Midjourney, actually they created a image that's, through this image, they reveal that they illegally used some data that has been has not been public, and because of that, they have some issue. So these are things that sometimes cause concern. However, we should have this in mind that these tools are very valuable, create a lot of opportunity. If they can save medical expert time, that's great. And we should all remember this. These tools don't need to be fully automated. Still, if you want to, for example, a radiologist want to write a report, they have, they can, using a short prompt, they can ask for a comprehensive review. And if we see some, the radiologist sees some incorrect information, they can correct it. So at the end of the day, these are tools to help us, and I don't foresee them to replace any of the medical experts position at all, because we are far away from that point. And I would like to hear your insights, Susan, as well.
Thank you both. Yeah, that was great. I think my biggest concern around, and this goes for natural language processing, but also for image analysis, is setting clear quality and safety parameters for the use of these. That's something we really haven't as a profession addressed. I know the American College of Radiology has been having some think tanks to sort of put these ideas on paper and really explore them so that we can address them systematically. But there are, as you said, wrong answers that pop up, bias that's intrinsic to all of these algorithms that just, we can only overcome to some extent. But clear quality parameters: when are these applicable, when are they not, when are they failing, what is the process for QC, like sort of an MQSA for algorithms. I've said that this is very important because I think we need a way of standardizing our approach to make sure that they're safe, because setting them loose on the public is ill-advised until we better understand their performance. Well, I think we're at the top of the hour, so thank you everyone for your attendance. We really appreciate it, and I hope you all have a wonderful rest of your day. Thank you.
Have a good day.
Thank you. Bye-bye.